right, welcome to our first lecture on acids and bases and how they establish equilibrium. So how basically extension of our equilibrium unit to specific cases of acids and bases. We'll do this lecture in two parts. The first part we'll talk about basically what acids and bases are and pH scale and how to do some calculations of pH and other things like that. Okay, so you're probably most familiar with the Arrhenius definitions of acids and bases. The Arrhenius definition of an acid is something that releases hydrogen ions. They react with carbonates or bicarbonates to create CO2. A base is something that, similarly when dissolved in water, increases concentration of hydroxide ions. These guys tend to taste bitter or feel slippery. Most soaps feel slippery, and most soaps are basic pH. We're mostly going to deal with what's known as the Bronsted-Lowry definition. So in this case, the acid is anything that can donate a proton. Still usually going to be H+, but it can be anything that's a proton. A base is anything that can be a proton acceptor. So in this case, we'll think of the base as a lot more as other negative ions that can accept a proton. So a Bronsted-Lowry acid must have a removable proton, an acidic proton, and the Bronsted-Lowry base must have a pair of non-bonding electrons that can accept something. If it can be either, it's called amphiprotic. So these are some examples of things that are amphiprotic. The one that we're going to deal with most often is H2O. It can be an acid and a base. So what happens when an acid dissolves in water? So basically, water can act as a Bronsted-Lowry base and take a proton from the acid. And so as a result, the conjugate base of the acid and a hydronium ion are formed. So if we're looking at something very common, like HCl plus H2O, you're going to yield Cl minus, which is going to be the conjugate base, and H3O plus, which is called hydronium. In most cases, we can use H3O plus or H plus sort of interchangeably. When we talk about the concentration of H plus increasing, an example of an acidic solution, we really talk about H3O plus increasing. So what is a conjugate acid or a conjugate base? Comes from Latin, meaning to join together. And basically, whenever you have a reaction between an acid and base, you're always going to get their conjugate bases and acids. So in this case, we've got NO2 nitric acid, and if this is the acid, water is going to be acting as our base. When we take away that H plus ion, all right, we're left over with NO2 minus. That's the leftover. That's its conjugate base. And then water is the base. We're going to add a hydrogen to it and get H3O plus. So the conjugate acid of water is H3O plus. So a couple examples. Think about these. I'll give you a second to think before we move on. What's the conjugate base of pH4 plus? Go ahead and pause and think about that for a sec. So hopefully you came up with pH3, right? So the conjugate base is what's going to happen when you remove a hydrogen ion. We would be dropping down to H3, and we lost our plus. So similarly then, what is the conjugate acid of SO4 2 minus? So this one we're going to be adding hydrogen to it. So it's 8 SO4. We had 2 minus before. Now we only have 1 minus. Strong acids, something we've talked about before. These are acids that dissociate completely in water. Right? Their conjugate bases are quite weak, so they don't really accept or donate protons, versus weak acids only partially dissociate in water. So in their case, the conjugate bases are weak bases, and so they do still accept or donate protons. So if it doesn't really do anything to the acidity, that means it's not really dissociating much in water. It means their conjugate bases are very strong. We'll talk about what that means in a second. So basically what that comes down to when I talk about their conjugate bases being very strong, in an acid or base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. All right, so let's think about this for a second. You got HCl, it's a strong acid. H2O is going to be the base. Here's your conjugate acid. Here's your conjugate base. Okay. H2O is a much stronger base than Cl minus, so the equilibrium rise so far to the right that K is not measured. Okay, that means that the way this reaction is written, right? This reaction would much rather happen. This H would much rather go to the H2O. This is a better proton acceptor than the Cl minus is, and so you're going to end up with H3O plus and Cl minus. If you look back at this chart here, you see Cl minus very, very, very weak base versus H2O. So you're not super strong, but it's still stronger than Cl minus. So the hydrogen would rather go to the H2O plus and make H3O plus than Cl minus. So in fact, in this case, it's a strong acid, so it's completely dissociates. So basically all of the HCl is going to turn. This reaction is going to go all the way over here to the right. Again, or similarly, if we're talking about a weak acid now, so this is acetic acid. This is something you should become familiar with. So we've got acetic acid plus H2O. So this is still your acid. This is still your base. Here's your conjugate acid. And here's your conjugate base. So in this case, the equilibrium favors the left side, right? So the acetate is a better base than the water is. So yes, some of it's going to go over here to H3O plus, but most of it would rather stay here. So the equilibrium lies to the left. Most of it's going to stay here as opposed to the way the reaction's written, in H going to the H2O and forming an H3O plus. Kind of strange, but I think it'll become familiar to you. Some cool things about water, like we said, it's amphiproteric. So basically, when you have water, some can act as a base and some can act as an acid. At room temperature, only about 2 out of every 10 to the 4th H2O molecules do this. So it's very, 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 very small percentage. But this is called autoionization. So you could have an H2O plus an H2O, and you could end up with H3O plus and an OH minus. So you can get a little bit of both. Well, why is that cool? Well, this process, if we're going to think about it this way, we could get an equilibrium expression for this process, right? H would be Kc, the concentration of H3O plus times concentration of OH minus. If you go back and look at this again, aqueous, liquid, these guys don't matter in the equilibrium expression. So it's just the concentration of our two products. So this is a special form of an equilibrium constant, and we call this the ion product constant for water, K with a subscript W. And so at 25 degrees C, room temperature, Kw is 1 times 10 to the negative 14th. This is going to be really handy to know. This is on your formula sheet from the AP board, so you'll have it on the test, but this is one of those things where if you know it off the top of your head, you're going to be a little bit better off. pH is defined as the negative base 10 log of the concentration of hydronium ion. All right, so pH is a negative log of H3O plus. Again, you can also just say H plus, and it's basically the same thing. So in pure water, your Kw here we just talked about, concentration of H3O plus, concentration of OH minus is 1 times 10 to the negative 14. Whoops. So in pure water, H3O plus, the concentration of H3O plus is going to equal the concentration of OH minus. So therefore, the concentration of H3O plus is just the square root of 1 times 10 to the 14th, which is 1 times 10 to the 7th, negative 7th. So in pure water, the pH of that is a negative log of 1 times 10 to the negative 7, which is 7. So in case you're ever wondering why, when you talk about pH scale, you probably knew that 7 was neutral, that's why. The pH of pure water is 7.00. An acid is anything that has a higher H3O concentration, so its pH would be less than 7, and a base has a lower H3O plus concentration than pure water, so its pH is greater than 7. So just a couple common substances and their pHs. Human blood here, slightly on the basic side. Again, some soapy things like borax is used in a lot of cleaners. That's pretty basic. Bleach and ammonia, 2 household cleaners, very, very basic. Versus some acidic things, you probably knew like black coffee or coffee is acidic. Tomatoes are pretty acidic. Lemon juice, 1 times 10 to the negative 2, which is a 2 pH. Stomach acid, you're approaching 1, so very, very basic. Very, very acidic. So an example, what can we do with this information? What kinds of questions might be asked might you be asked to do? So calculate the concentration of a hydronium ion in a solution in which the hydroxide ion concentration is 0.010 molar, assuming the temp of the water is 25 degrees Celsius, which it pretty much always is going to be in these cases. So how can we do this? Well, you know that the concentration of H times the concentration of OH equals your Kw, 1 times 10 to the minus 14. Therefore, your concentration of H is 1 times 10 to the negative 14 over the concentration of OH, and you know the concentration of OH from the problem, so this is what you get. Concentration of H plus ions is 1 times 10 to the minus 12 molar. The P in the pH tells us to take the negative base 10 log, like we said. In this case, it's going to be the hydronium ions, but you can also do the same thing with OH. So the POH is just a negative log of the OH minus concentration, or the PKW is a negative log of KW. So whenever you see that P, that just means negative log of something. So why does that matter? Well, okay. Concentration of H3O plus times concentration of OH minus is your 1 times 10 to the minus 14, like we said. And so you can take the negative log of both of those equals the negative log of Kw, which is 14. So that basically means then that pH plus POH equals PKW, which is 14. Pretty nifty, huh? So if you know the pH, you can figure out the POH. So a sample of freshly pressed apple juice has a POH of 10.24. Calculate H plus. How can we do that? I'm going to let you pause and think about that for a second. Okay, hopefully you've thought about that for a second. So what are you going to do? Well, we can figure out our pH relatively easily. pH plus POH equals 14. So pH equals 14 minus our POH. So our pH is 3.76. Once you have your pH, it's very easy to calculate your H plus ions. pH is just the negative log of your H plus ions. So log of H plus equals negative 3.76. And the concentration of H is then the antilog of negative 3.76. So that's 10 to the negative 3.76. So our concentration of hydrogen ions is 1.7 times 10 to the negative 4 molar. Pretty cool. How do we measure pH? What are the different ways in which we do this? Well, there's a bunch of different ways. If you're really just kind of looking for more of a qualitative, is it acidic or is it basic, you can use litmus paper. So you can have red litmus paper turns blue in basically basic pHs, and blue litmus paper will turn red in acidic pHs. You can see they're not perfect, right? If you had something that was like 7.2, it's not really going to change in either of those. There are different indicators you can use. So different indicators will change color at different pHs. You can use universal indicator, which is basically all of them mixed together, and you can kind of get different color changes at different approximate pHs. You can even get what looks like litmus paper indicator paper that would be impregnated with all of them. So you could dip the paper in your solution and get a rough estimate of what the pH is. If you want more accurate measurements, we use a pH meter, which just basically measures the voltage of a solution and correlates that with the concentration of H plus ions. So we'll be using these in some labs in this unit. All right, so strong acids. Hopefully you remember the 7 strong acids: HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. So these are, by definition, strong electrolytes. And so what makes them strong is whenever you mix them in a aqueous solution, they're going to be totally dissociated. You put HCl in water, and you're not going to have any HCl together. You're going to have H plus ions and Cl minus ions. And so, for the monoprotic strong acids, the concentration of H3O plus is just the concentration of acid, because all of that acid dissociates, which is handy to know. Strong bases, very similar, are the soluble hydroxides, which are the alkali metals, and the heavier alkaline earth metals, calcium, strontium, and barium. And again, these things totally dissociate completely in aqueous solutions. So the same thing, the concentration of the base is going to be the concentration of your OH ion. So for a generalized acid reaction, we can calculate what's called the dissociation constant. So this is basically like the equilibrium constant to see how much of your acid is going to dissociate, what percentage of it is going to turn into ions. So if this is our generalized expression, you see this all the time. This is your acid over here, plus your H2O in this case is the base. Here's your conjugate base, in your conjugate acid. So the equilibrium expression then would be the concentration of H3O times the concentration of your conjugate base over the concentration of your acid. Again, this isn't going to count because this is a liquid. So this is called the equilibrium constant, the acid dissociation constant, and we call this Ka with a subscript A. The greater the value of Ka, the stronger the acid. Remember, greater the value, that means you're getting more products, so you're shifting the equilibrium more to the right. So larger Ka means you're shifted farther to the right. Strong acids are very far over to the right. They're all products. Versus a weak acid like acetic acid is going to exist mostly in acetic acid form and a little bit of acetate and hydrogen ions. So this has a pretty small Ka. So you can use pH to figure out what your Ka is. So let's check out an example of that. The pH of a 0.1 molar solution of formic acid, which is HCOOH, is 2.38. Calculate Ka for formic acid at this temperature. Okay, so we know, right, we have our equilibrium expression. Ka is going to be the concentration of H3O plus, and your formate ion, HCOO minus, and your concentration of formic acid. So to get Ka, we need to know the equilibrium concentrations of all these three things, right? Maybe you see where this is going. This might seem familiar to you. So we can find H3O plus from the pH because it's going to be the same as the concentration of HCOO minus from the pH. Okay, so pH is a negative log of H3O plus. So 2.38 is negative log of H3O plus. 10 to the negative 2.38 equals 10 to the log. So 4.2 times 10 to the minus 3 equals our concentration of H3O plus, which is the concentration of HCOO minus. Remember, they're going to be dissociated equally. For every H3O plus you're making an HCOO minus. So now we can set up our good old ice chart. So initially we knew we had 0.1 molar of the formic acid, none of our conjugates. And we figured out how much we made. We made 4.2 times 10 to the minus 3 molar. Same thing over here, which means this one must have decreased by that much. So now we know our equilibrium concentrations. Since this is such a small amount, right, 0.1 minus 4.2 times 10 to the minus 3 with sig figs is still just 0.1. So basically this hasn't really changed at all for all intents and purposes. So we can just call it 0.1. So now we can plug that into our equilibrium expression, and we can get our Ka, 1.8 times 10 to the minus 4th. You can then use this to calculate percent ionization. And as you'd expect, this should be a pretty small number because this is a weak acid. So you just get your concentration of H3O plus at equilibrium over your initial concentration of acid times 100%. And so in this example, we had 4.2 times 10 to the minus 3 molar. Initially, we had 1.1 molar. You get 4.2%. So a very small amount ionized. It's a weak acid. This is what you'd expect. It's mostly going to stay in the formic acid form. Very little of it, 4.2%, is going to turn into the ion form. You can also go the other way. You can figure out the pH from the Ka. So in this example, we're going to calculate the pH of a 0.3 molar solution of acetic acid at room temperature. So here's your reaction. Your acetic acid plus water yields H3O plus your acetate ion. And the Ka for acetic acid is 1.8 times 10 to the minus 5. So what are we going to do with this? Okay, equilibrium expression, which you should be able to be pretty familiar with by now. So we've got that. Great. All right, now what? All right, set up our table. We know our initial amounts. Okay, 0.3 molar. We don't really know how much things change, so we're going to use x's. We know from our equation that they're all stoichiometrically equal, so plus 1 and minus 1 in each. And so here's your values. Here's a cool trick that we can do, though. For most weak acids, they dissociate very little, like we just saw. So we can assume that x is going to be very small, especially compared to 0.3. So then basically, it doesn't matter. With sig figs, it's the same thing. So it's going to stay as 0.3. You can do this, you can make this assumption if your percent ionization is less than 5%, or if your Ka is less than 10 to the minus 5. Whenever you're given a problem like this on the AP exam, you're going to satisfy these conditions, so you don't have to really worry about it too much. So How do we do this? So we just plug these values in. 1.8 is our Ka in our x squared, so the concentration of our H3O plus our conjugate base. Here's our initial concentration is 0.3. Solve for x. X is 2.3 times 10 to the minus 3. That then is our concentration of our H3O plus. So the pH is just the negative log of that. So our pH of the solution is 2.64. So still pretty acidic, right? Just because it's a weak acid doesn't mean that it's not going to be very acidic. This is still quite acidic. All right, now I want you to try this one. I'm gonna ask you to check out the question, pause it, and try it on your own, and then come back to the video when you're ready to see if you did it right. So go ahead, pause, and figure it out. Okay, hopefully you came up with an answer that seems to make sense to you. So what are we going to do here? We want to get the pH of this solution, and we know the Ka. So this is very similar to the one that very similar to the one I just had you try. Okay. So we've got our chemical equation: hydrocyanic acid, dissociation H+ and cyanide ions. So you need to get your equilibrium concentrations. So hopefully you set up an ice table. So X is going to be our concentration of H. So initially we had 0.2 molar, we had none of this. We don't know how much this changed, but we do know they're equal amounts. So this is 0.2 minus X. We're going to put this into our equilibrium expression. So X times X, and 0.2 minus X. And we can use our little trick. So K was still very small. It was much less than 10 to the minus 5. So we can assume that this X is negligible. So we can just assume 0.2. So x squared is 0.2 times 4.9 times 10 to the minus 10. And it's 0.98 times 10 to the minus 10. So that's our concentration of H+, right? So now we just got to get our pH for that. Solve for pH is the negative log of that. So negative log of 9.9 times 10 to the minus 6. pH should be 5.00. So hopefully that's what you got. And the last thing for this video, polyprotic acids. These are acids that have more than one acidic proton. Okay, so if you look down here, like carbonic acid, H2CO3, you've got two H's that you could potentially give up. Because that they have two dissociation constants, right? Because they're going to dissociate twice. If the difference between the first and the second, or the second and third, or whatever the subsequent Ka's is greater than 10 to the third, then you can pretty much just call the pH is really just based on that first dissociation, because it's going to be not a whole lot of that second one is actually going to be dissociating. So that's a nice little trick that you can use. But some acids, again, can do more than one proton. You don't see these as much on the AP board. And that is that for this video.